Hi, I'm Mike Marin, and in this video we'll discuss the idea of polynomial regression and how to fit and assess these models in R. Polynomial regression is a special case of linear regression where the relationship between x and y is modeled using a polynomial rather than a line. It can be used when the relationship between x and y is nonlinear, although this is still considered to be a special case of multiple linear regression. We will be working with a different version of the lung capacity data as was used in other videos. A link to download this data can be found in the video description below. You can also download the R script used in this video there as well. I've already imported the data into RStudio and attached it. As an example, we'll model the relationship between lung capacity and height. Let's begin by looking at a scatter plot, and let's fit a simple linear regression model and look at a summary of that model. Here we'll model the relationship between lung capacity and height. We can take note that the R squared is about 75% and the residual standard error is 1.292. We can also add the line for this model to the plot using the AB line command. Visually, we can see that the relationship between lung capacity and height looks a bit curved or nonlinear. A reminder that we can also use residual plots to help with assessing linearity and checking model assumptions. For a more thorough discussion of this topic, you can refer to one of our earlier videos on checking assumptions for linear regression. There are many approaches to dealing with nonlinearities. One we will discuss in this video is including polynomial terms in our model. We will start with including height squared in our model. First, let's take a look at the wrong way to do this. While it may seem like including height squared directly in the model call will work, R will not include height squared in the model if entered this way. Let's take a look at that. Here we can see if we enter height squared directly in the model call, in the model summary you can see height squared is left out. R has just ignored height squared. It is important to take note of this because R does not give us a warning or an error message with this. Now let's take a look at the right way to do this. To do so, we'll use a capital I and then include height squared within the parentheses. And if we ask for a summary of the model, we can now see that height squared has been included in the model. We'll get to talking about this model in a moment, but first, let's take a look at a few other ways to get the same result. Instead of using the approach we just showed, we could instead first create a new variable called height squared, and then include this variable in the model. Here we can see we're creating this height squared variable and including that in our model. And if we ask for the summary, you can see that this produces the exact same model and results as the previous set of commands. We could also make use of the poly command in R. Here we would let R know that we would like to include polynomial terms for the height variable, and we set the degree argument to the degree of polynomial we'd like. In this case, setting the degree equal to will include height and height squared. And if instead of setting the raw argument to true, we set it to false, R would fit a model that used orthogonal polynomials. So let's fit that model. And again, you can take the time to verify that this produces the exact same results as the earlier two ways we looked at. So let's just give ourselves a quick reminder of the model that we fit. We can see here that with this polynomial including height squared, the R squared is about 77% and the residual standard error is 1.238. You may recall that for the model with only height, the R squared was about 75% and the residual standard error was 1.292. It looks like height squared may be improving the model. Let's take a look at this visually. We can add the polynomial model to the plot using the lines command. So let's add this line using a thick blue line. Subjectively, it looks like the model that includes height squared may provide a better fit to the data than the model that does not include height squared. Let's compare these two models formally using the partial f-test. For a more detailed discussion of the partial f-test, you can see one of our earlier videos where we discussed this test. This test has a null hypothesis that there is no significant difference between the two models, and an alternative hypothesis that the full model, the model that includes height squared, is significantly better. We can run the test in R using the anova command. We can see that with such a small p-value, we will reject the null hypothesis and conclude that we have evidence to believe the model including height squared provides a statistically significantly better fit than the model without height squared. Most often, we won't want to include polynomial terms much beyond x squared or x cubed. Let's explore a model that includes x cubed as well. And it's worth noting that you must always include all lower order terms in a model. If we include height cubed, we must also include height squared and height in the model. Let's fit this model, including height squared and height cubed. And let's ask for a summary. We can add this model to the plot using the lines command, and we'll do this as a thick green dashed line. Let's also add a legend to the plot to help remind ourselves which model was which. We can see visually that there's almost no difference between the model that includes height cubed and the model that does not. As before, we can use the partial f-test to help us decide if height cubed improves the model. Here, when we conduct the partial f-test, we can see that the p-value is large and there is not a statistically significant difference in the models. We can decide that including height cubed is not necessary in our model. Before finishing off, we should add a note that there are other approaches to dealing with nonlinearities, some of which include transforming the x or y variable, converting x to a categorical variable or factor, or using nonlinear regression methods instead. All of these different approaches have their pros and cons. Thanks for watching this video. Make sure to subscribe to our channel, like us on Facebook, visit our website, and check out our other instructional videos.